So today what we're going to do is do a little review of titration, because on Tuesday you will be doing a titration lab. Some of you did a titration last year, some of you did not. That's okay. I have a procedure for a titration that will walk you through it step by step. I've even had grade 9s do it successfully using it, so it'll walk you through it. It's all good. We're going to take a brief look at this and at the calculations involved. Okay, and I need to find a glove. Where's my glove? Gloves? No. No. Great. That's okay. Okay. So, I don't know what this pipette safety filler thing is. I stole this image from somewhere. We are going to use a pipettor. Is there anyone in here who has not used a pipette before? Okay, I'm going to give you a very brief little demonstration, because there is a way of hurting yourself with this. Okay, so here's a pipette. Make sure when you put a pipette down on a desk, it's never like this way. So it'll roll off the desk. Make sure it always goes in between a couple things so it does not roll off the desk, or you can have it attached to this, and that will also make it not roll off the desk. Now, if you take the pipette and you hold it in the middle, you have a big, long glass piece, yes? Which is very what? Breakable. And if you then go and you jam this on here, it is possible for you to break it. And then as you're pushing it on and jamming it on, cuts right across your hand, bleeding, sadness. It has happened. I've only had students injure themselves seriously twice, and this was one of them. Okay, they had to go get stitches. Now, just hold it up here, because it's really hard to break a small piece of glass, right? Have you ever tried breaking a short stubby pencil in half or something like that? It's hard to break it. But if you have a big long pencil, it's much easier to break it because of levers and stuff like that. Yes? So all you do is you put it on like that. And next day I'll give you a little lesson on how to use it personally, if you need to like figure out how to make it work. Okay? But yeah, that's a safety one that everyone needs to know. We have a conical flask. What is another word for a conical flask? Tell your partner. Also known as an Erlenmeyer flask. Yes. Now, the solution that we put into the Erlenmeyer flask this solution is usually unknown concentration. And because it is unknown concentration, the purpose of the titration is to analyze it and find out the concentration. So we are wanting to analyze this thing to find the concentration. And so the name of this solution is called the analyte. It's the thing we want to analyze. So for example, in this particular lab that we are going to do, we are going to have an acid in here. Okay, and the acid has an unknown concentration. We are also going to add a few drops of an indicator. Is there anyone in here who has never had any experience with an indicator, like never used one? Okay, don't worry. We'll get practice with those. Okay, but an indicator is something that turns one color at one pH and a different color at a different pH. The indicator we will be using is called, and you don't have to be able to spell this, and I'll tell you why in a minute. It's called phenol. I'll just leave that part there for a minute because the rest of it gets really nasty. And then we have a pH. And then we have a TH. Phenol phthalate. And I don't know if any of you have seen Sylvester the Putty Cat. Have you guys seen Sylvester the cat from Looney Tunes? Yes? Phenolphthalein. Okay? Phenolphthalein. Yeah. Oh, I forgot the A. There's an A. Phthalalein. Phenolphthalein. Phenolphthalein. And we actually just don't pronounce the pH. We just say phenolphthalein. Unless you really want to say phenolphthalein, which is kind of fun, but you know. Phenolphthalein. Phthalate. Now, you don't need to be able to spell this because guess where we have it written? On page 7, we have a whole list of, this is your data booklet, of acid-base indicators. And if we go down here, we're like, oh, look, here is phenolphthalein. And its two colors are colorless and pink. So, phenolphthalein is colorless in acid. And it is pink in base. Okay, colorless in acid, pink in base. So right now we have an acid solution with a little bit of phenolphthalein in it. What color will it be? Colorless. Then what we're going to do is we're going to take our flask, we are going to put it underneath a, what do we call that big long tube? Volumetric pipette. No. We're going to put it underneath, this is a volumetric pipette, okay, and this is what we use. We use the volumetric pipette to measure out the acid and put it into the flask. Okay, and then we put this away. All right? Then we go and we get a burette. Grab one of these. Anybody not used one of these? That's okay. You will get you all set up on Monday. Okay, so we have the burette. It starts at 0 and it finishes at 50 milliliters. Okay, so up here we have 0 milliliters and down here we have 50 milliliters. Don't try and do anything fancy like subtracting the volumes. Just read it directly off. It reads downward. And the reason it reads down is you'll take your final volume and subtract your initial volume, and that will tell you how much you dripped out. Okay, so if you start at 0 and you finish at 12, 12 minus 0 is 12. Okay? Now, in this burette, we are going to have our known concentration solution. And this is called the titrant. It's called the titrant because we titrate the acid with it. Yes, we're titrating with this solution. So, for example, in this one, this is going to be what would we react an acid with? A base. Yes. All right. So we've got an acid down here. And into it we are dripping a base. So who are the two reactants in the reaction that is occurring in that flask? We have an acid plus a base. And do you remember the products of an acid plus a base? Water. We get water plus a salt. What type of reaction is that? That is neutralization. Now, let's say you had 3 moles of acid, okay? 3 moles of acid. And let's say that every drop of base contains 1 mole of base. Are you with me? 3 moles of acid, each drip contains 1 mole of base. So I drip in 1 drop of base and it neutralizes that 1 mole of acid, and now I only have 2 moles of acid. What color is the solution still? It's still colorless because I still have acid. Now I drip in another drop of base. Oh, I better do this one, otherwise it could be rude. Okay, I drip in another drop and that neutralizes it. Okay, so now I still have 1 mole of acid. Yes? So what is the color? It is colorless. And now I drip in 1 more drip of base. What's my pH now? 7. pH is 7, and if we look at phenolphthalein, it changes color in between pH 8.2 and 10.0, so it is actually still colorless, okay? But now I add just the tiniest little bit more of the base, and all of a sudden, I have base. Yes? So before I had excess acid, and then I had a neutral solution, and now I have base. And as soon as I have base, the pH is going to spike, all right? And we will have a pH above 8. So it will turn what color? It will turn pink, okay? So that is how you're going to know that the reaction is complete. Because what's happening is you're saying, I've got 3 moles of acid. I had to add 1, 2, 3 moles of base plus a little tiny extra bit more. And to be honest with you, that little tiny extra bit more is not enough in terms of volume to make any difference. Like going from neutral to excess base is like such a small volume, you can hardly tell the difference. Okay, so we will know that we have exactly reacted all of the acid with all of the base, and that the moles of H plus is equal to the moles of OH minus when it turns color. Okay, so let us see what it actually says here. This is just a description of what we have talked through already. We measure a known volume, usually 10 or 25 milliliters, because that's the size of pipette we have, and we put it into the Erlenmeyer flask. And usually this is the thing where we have the unknown concentration. What do we call the thing with the unknown concentration? We call it the analyte, because we are analyzing it, yes? We place our other solution, the one where we know the concentration, into the burette. So the titrant, the one where we have the known concentration, goes in the burette. This is not always the case. Sometimes you do put the unknown in the burette and the known in the flask, but we're not going to worry about that. These are going to be simple ones. We add a few drops of indicator to the flask. And then we carefully open the tap on the burette. Okay, so the burette has a little tap on it. Now, to be honest with you, I think they call it a tap in Britain, but I have never heard that term used in like my university. Maybe they've changed, because the word that I heard used was stopcock, which is an unfortunate name. So if you prefer to call it tap, you can call it tap. Okay? But I want you to know that word, because that might be how you hear it referred to in university. Okay? All it is it's this little thing here that you can twist around. If it's up and down, that means water is going to drip out. Solution is going to drip out. If it is parallel to the ground, that means it's going to stop the liquid from dripping out. So you never want it to be like this unless you want dripping to occur. Okay? All right. So we drip it out until the indicator just changes color. Now, you can get shades of pink, everything from this color to this color to even lighter, where you can only barely see the pink color and you kind of have to look at it sideways and you're like, oh, is that pink? Is it? Yes, it is. Oh my gosh, I can hardly tell. You are aiming for this color or the one where you can hardly tell that it's pink. Okay? Those are good colors. This color is the color of shame. Yes? I'm kidding, because this is the first time you've done a titration. You will get that color. Okay? It will happen. And in fact, I'm going to tell you why you might actually want to see that color in your first run. Okay? But we'll get to that. Now, you're going to do this once. I don't know if any of you have done any data analysis in math. If you're running an experiment and you only do it once and you get a number once, how good is your data? Yeah, not very good. Like, it's like if you did a poll of people and you only polled one person, your data would not be so good. So you are not just going to do this once. You're going to now wash out your flask and repeat. Okay, and you will repeat it until you get at least 3 concordant results. What the heck is a concordant result? Concordant results agree within 0.2 milliliters of each other. Okay, so they should all be within 0.2 milliliters. Now, this is maybe for some of you your first titration ever. Some of you did it last year, but you haven't practiced it in at least 6 months. So chances are you might not get results within 0.2 milliliters of each other. You might only get 2 concordant results, and that will be okay. Yes? You may only have things within 0.5 milliliters of each other, and because this is your first titration or second titration, you're going to say, that's okay. We're going to go with it, because we're really just learning the procedure and how to do the calculations. Okay, in an ideal world, you will have at least 3 concordant results, but we might not get ideal results on Tuesday. Okay, the other results, we often call them outliers because they lie outside of our good data. Okay. All right, now let's look at what we're going to record, because you guys are going to be responsible for recording your data. Your burette readings, both the initial and the final burette readings, should be recorded to a precision of 2 decimal places. Okay, on Tuesday, I will show you how to read a burette using a burette reading card. Okay. In general, in North America, we call them trials. I steal resources from a lot of British websites because they do a better job at teaching chemistry than we do, I think, a lot of the time. So they use the word run instead of trial. So if you see the word run, it just means trial. Trial 1, trial 2, trial 3. The first trial. There you go. Okay. Where did we get to here? Yes. The first trial. So the very first one you do, you have no idea how much volume it's going to take to get to your pink color, right? You don't know. So you could spend a lot of time going drip, 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 drip. Swirl. Oh, didn't change color yet. Drip, 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 drip. Swirl. Oh, it didn't change color yet. You could spend 20 minutes doing that. Yes? And you might not discover that you get there until 10 milliliters or 20 milliliters. You just don't know. So one thing that you often do to make it efficient is for your first run, you make it a rough trial. Okay, so you open up the tap, you swirl, your tap is open, and you're like, oh, it's really pink, and you turn it off, and it is that pink color of shame, except for it's your rough trial, so it's not really a color of shame. Yes? What you would be doing is you would be saying, perhaps I have my burette. Do I have a place I can do this? Perhaps I have my burette and I start at 0. Whoops, that says 10, not 0. Let's say I started at 0 milliliters. And let's say I ran it down to 10 milliliters and I got my bright pink color. Right? And that's trial number 1. That's my rough run. Okay, my rough trial. Next time, I know that 10 is too much. So what I'm going to do is I'm going to drip out slowly. Yes? Or I'm going to drip quickly until I get to about 8 milliliters. Right? A couple milliliters before that, which would make 18. And it will still be, so this part I will do fast, and then the last couple milliliters I will go slow. Does that make sense? So now what you've done is you've done this one fast, and you're like, I'm just getting a ballpark of where it is. And then my second one, I go fast till when I'm within about 2 milliliters of that, and then I can go slower to get that nice light pink color, right? So hopefully down in here somewhere, I get my lovely light pink color. Yes, maybe at, 19.5 milliliters. Yes? And then if I get my nice light pink color at 19.5, I know my volume is going to be about 9.5 milliliters. So I can say for my next run, what's 19.5 plus 9.5? Right? 28? Okay, so what I'm going to do is I'm going to go to 28, and then I'm going to be like, okay, and now I'm going to go almost to 28 and then go really slowly. So I can get like within 0.5 of that. So I can still go, it makes the beginning part of the titration quick, and I only have to go slow for the last part. Yes? Okay. Now, here is some sample data. Okay, you can see all our results are recorded to 2 decimal places. All right. They actually have a typo in here. Whoever made this should say 1. Okay. And the reason it should say 1 is because we are starting our next run at that volume. So we start at 0, we run to 23.15. 23.15 minus 0 is 23.15. You do not need to refill the burette again because you know that 23 is not halfway to 50, right? And so if you're going to go another 23, that'll only take you to about 46. Yeah? When you get to 46, should you be refilling? Yes, because you won't be able to do a full run. Never try and do a titration by like doing the last little bit here, filling it up, because every time you make a measurement, you're introducing error. So you're going to try and keep it to 2 measurements per run. Okay? You can see our data here, 45.95 minus 23.15 is 22.80. Our run number 2. Oh, look, they didn't even start at 0.00. Do you have to fuss around and make sure you're starting your first run at 0? Do you need to make sure it's perfectly filled to the 0 line? No, you can start anywhere. Okay, you want to start near the top so you've got lots of volume, but it can really be anywhere. Okay, and then our final run, 23 went to 46.1. These 2 results are concordant. So we're going to put a check mark beside them. This one is too far away, and this one is too far away. Yes? So when we go to average our results, we will average these 2, which is going to be a really easy calculation because they're both the same. Is good? Okay. All right, we're going to do an example here. We have 0.2 molar NaOH is used to titrate 3 separate 50 milliliter samples of H2SO4. I would like you to tell me which substance is the titrant and which is the analyte. So tell your partner who is the titrant and who is the analyte. So we are analyzing our unknowns, so that's our analyte, H2SO4. And it is being titrated with NaOH, so that is our titrant. So now we are going to go on to the diagram, and we're going to label the titrant and the analyte with the formula of the chemical plus any numbers that are relevant, any concentrations or volumes. So the analyte is H2SO4. The titrant is NaOH. Do we know any numbers about the H2SO4?
Yes, we do.
What do we know about the H2SO4?
It is 3 separate 50.0 examples.
Okay, so we know that the volume of H2SO4 is 50.0 milliliters. Yes? Okay. Do we know anything about the NaOH? Yeah, we know that it is 0.200 molar. Okay, so we're going to write that down, 0.200 molar. You don't have to draw a diagram every time. I just like to have one this time because it is one of your first ones in a long time, or ever, possibly. So let's say you and your partners are doing this, and these are NaOH, trial 1. We start at 0, we finish at 9.02. 9.02 minus 0 is 9.02. Trial 2, we start at 9.02 because why refill the burette when we don't have to? And we finish at 17.95. 17.95 minus 9.02 is 8.93. And we do the same thing for trial 3, and then we do the same thing for trial 4. If we look at our results, we're looking for things that are within 0.2 milliliters of each other. 0.93, 0.94, and 9.02 are all within 0.2 of each other, yes? Okay. Is 9.18 within 0.2 of any of those?
Yes.
It is, but is it within 0.2 of all of them? No. So it's not good enough to be within 0.2 of one of them. It has to be within 0.2 of all of them. Okay, so this one is a no. So we're going to take those 3 and average them. I assume in grade 12 you guys know how to take an average of 3 numbers. Yes, add them up, divide by 3. Okay. 8.96 milliliters. Now we need to write a balanced equation. Who are the reactants in this balanced equation? NaOH and H2SO4. And what do we know about NaOH? What kind of a chemical is NaOH? It is a base, and what type of base is it? It is a strong base. How do we know it is a strong base? Metal hydroxides are all strong bases. Now, I don't need to know whether H2SO4 is strong or not. If at least one of these two is strong, what kind of arrow am I going to have? I'm going to have a single one-way arrow. As long as one reactant is strong, it will push the reaction to completion. Do you guys know how to predict the products? We get water and a salt. Now, I'm going to give you a little hint. If you have any difficulty with it, you are going to say, who is my ion here? Who's the cation? Na. And what's its charge? Plus. or plus 1. I'm going to put the 1 there because remember when you're writing a formula, you need to make sure the charges balance. Yes? Who's my anion here? OH minus. Who's the cation in H2SO4? H plus. And who is the anion? SO4 2 minus. Some of you might just be able to look at this and write the products by looking in your head, right? But if you have any trouble at all, you will combine your outside ions. Okay, so that's the Na plus and SO4 2 minus, and then you will combine your inside ions. Do you remember doing this with double replacements? Okay, and we're going to go backwards. And so we will end up with, what is the correct formula when Na gets together with SO4? Na2SO4. Sadly, I wrote that up there and made it cluttered, but that's okay. And then you have the choice. You can write H and OH as H2O, or if it makes it easier for you to balance, you can write it as H and OH. Up to you. If you find balancing easy without writing it like that, you can just write H2O. Okay? Could you balance this reaction?
Yes.
Yes? We need 2 sodiums. So let's throw a 2 on here. And whenever you're balancing neutralization, the number of hydroxide and the number of hydrogen and the number of waters will all be the same. And you'll notice, how many hydroxide do we have? We have 2 hydroxide. How many hydrogen do we have? 2. So how many water do we need? 2. Okay? So it's pretty straightforward. And the reason we need this equation is that when we go to do the calculation, we will be doing some stoichiometry. What do you need for stoichiometry? You need a balanced equation so that you have the coefficients, yes? All right. So let's look here. From the previous page, I've brought over the data. We have 8.96 milliliters of NaOH. We have a balanced chemical equation here with a 1 in front of the H2SO4 and a 2 in front of the NaOH. I don't really care about the products. I mean, they're nice, but whatever. Now, whenever you do stoichiometry, the key part is going from moles of A to moles of B. And where do you get the numbers to do this? You get them from the coefficients. So if you don't have a balanced equation, you cannot do this. So anytime you're doing a titration, you must make sure you have a balanced chemical reaction. You're going to start with the information you have about your known substance. Okay, we know we have 8.96 milliliters, and we know we have 0.20 moles per liter. Can we use that to find moles of NaOH? Would you be able to find moles of NaOH given these? Yes. You know you would have to convert 8.96 milliliters into liters. Do you guys know how to do that? How many places do you move your decimal? 3 places. So it would become 0.00896 liters. Yes? Okay. Now you have moles of NaOH. You're going to use your coefficients to find the moles of your unknown substance, the H2SO4. And then finally you say, oh, what does the question actually ask me for? It actually asks me for the concentration of H2SO4. So I need the moles of H2SO4, and then I need to divide by the liters of H2SO4. You can do it all in one line if you want to. You can say, I want to find moles of H2SO4, and I want it over liters of H2SO4. I am starting with, why you not behave? Okay, there we go. Seriously? Okay, let's try this one, see if this one works. No, okay, let's try this one, see if this one works. Okay, there we go. Okay, so we have liters of NaOH, and we need to cancel with liters. Now that gives us moles of NaOH, yes? Moles of NaOH will cancel with moles of NaOH. And where do we get this number 1 and 2 from? Where do those come from? Those come from the balanced equation, okay? That gives us now moles of H2SO4, which is what we wanted to have on the top, yes? We wanted moles of H2SO4 on the top, and we want to have liters of H2SO4 on the bottom, and we know that we have 500 milliliters of H2SO4, yes? So we're going to put our 500 milliliters on the bottom. Is it okay that this one is just hanging out here with no unit? Absolutely, because we don't actually want to do a conversion, we want to do a division. Yes, and this is a way of showing it all in one line. Let's say you don't like that. You're like, I don't like that one, it's hanging out there, it's confusing me. You could do it where you find moles of H2SO4 by doing that same calculation, but you would find moles of H2SO4 and then do the concentration on a separate line. I would like you to look at the next method and tell me why it is not okay. What is wrong with this one down here? Mm-hmm. Do you see how 0.896 times 0.2 times 1/2 is equal to 0.00896? Yes? Is it equal to 0.00896 divided by 0.05? No. That would be like writing, okay, I have 3 times 2 is equal to 6. But now I want to divide that number by 4, so I just go like that. Right? That would not be a happy thing. Yes? So you would need to do that on a separate line, or you would need to do 3 times 2, and then you could do times 1/4, which is what we did in the other situation. Okay? And then you could say, oh, that's equal to 6/4, and there we go. Okay? Is good? All right. I'm going to leave that. You have practice quizzes. You have, hopefully everybody has the review, the overall review. I seem to have a lot of copies of these. Is there anyone who did not get this? Everybody got the overall review? Okay. Whatever. All right, and so the rest of class is a work block, okay? Or a falling asleep block. I understand. Friday afternoon, it's very difficult.